Hello, this is Puya. Today we're gonna see what recursion is, and we're gonna see like C++ recursive functions. Uh, uh, First, before we start looking at recursion, let's just do some review about function calls and like how the control moves when you call a function. So in this example, we have three functions, including the main function. In the first line of the main function, we want to print something, we want to see out something, and we call a function called cstring sequential search. We're passing two arguments to this function. So whenever a function is called, then uh, space in memory, in the part of memory called the stack, is going to be allocated to that function, and that space is used for the parameters of the function and the local variables for the function. So as soon as we go here, the control goes to the function, and so the argument is passed to this parameter, L is passed to this character, and these variables, these local variables of the function, are stored separately in a stack frame in the stack part of the memory. We have in the first line of this function, now we have uh, an initialization for a variable called size, and on the right hand side of the assignment operator we again have a function call. So as soon as you call a function, everything is going to be on hold, right? So the control jumps to the function, right? So again, another part of the memory will be allocated to this function call. So then you would have another variable s in this stack frame for this function. So these two variables, although they have the same name and although they're gonna have the same value, but they have two separate physical addresses in the memory, so they're not the same thing. And once this function finishes its operation, like here we just calculate the size of a C string here and we return the size. So once we return from the function, the um, the part of the memory that was allocated to this function, it was in the stack part, so like everything is going to be deallocated automatically. It's a static memory, so it's going to be it's non-dynamic memory, so it's going to be deallocated automatically, and the size is returned here. So then the function can continue, and then the control would come back here, and then it goes to the next line. It basically search for a specific character in the C string, and if it can find it, it returns the first index. If it can't find it, it will return -1. And again, once you return from the function, the part of the memory that was allocated to this function, it would be deallocated automatically, and then the control goes back to where the function was called, and now in the main function we can just print what was returned to from this function to us, and then it just like ends the program. So here, like, we wanted to review the concept of calling a function and how a separate part of the memory would be allocated to each function call, and how everything would be on hold until we return from the function that was called, and then the control would continue from where it left the function, right? So uh, as an example, I want to show you this example, another example, like with this time 4 functions including the main and like many function calls. So let's visualize this and see how this works. Just go back to first. So here you see that in the first line of the main function we call the nothing tree function. So the control jumps here. This is the memory space for this function call. So n is going to be initialized. In the first line of this function we call another function. So again, another part of the memory is allocated to this function call. N is going to be initialized. So that's what I meant. These two n's are different variables, right? So like we should not, this is local variable for this function, this is local variable for this function. In this first line of nothing to, another function call happening here. So like again, we're gonna go here, the control jumps here, so it's gonna print, it's gonna initialize n and then print 36. Now it's a void function, so it returns from it, it jumps here, this is done, so now it goes here, it's gonna print another thing, and then again it returns from this function. Now, so you saw that as soon as we return from the function, the stack frame that was allocated to the functions are deallocated automatically. Again, now that this is done, we can continue in this function. It goes to nothing 1, so it's gonna jump here again, another stack frame. It's gonna print one more number. It returns. As soon as it returns, this memory stack, this stack frame is deallocated. Another printing is happening here, and this is done. Okay, this wasn't recursion. The only reason I'm showing this so that like you see that how we would have basically a call a stack. So every time you call a function, would have a stack frame that would have all the local variables of the function, and this is how function call happens. Like, so this is just an introduction before we see what recursion is. So in the mathematical and computation sense, recursion is a solution to a problem where the solution itself is defined in terms of the problem and satisfies the following two conditions. Um, every time, like at every stage, the solution is defined so let me first go with the downsizing. So each subsequent self-definition of the solution approaches the stopping criteria. So we try to downscale the problem. We try to downscale the problem at each stage. We downscale the problem until we get to a point that we call a stopping criteria. At certain stage, the solution is defined explicitly. So basically, like we have a huge problem to solve, and what we do, we try to downsize the problem and make it like smaller and smaller and smaller until we get to a point that we know the solution explicitly, and that point is called the stopping criteria. So recursive functions or recursion has two stages, has two parts, sorry. Stopping criteria, which is like the smallest problem that we can get, and at that point we stop the recursion, we stop getting to a smaller point. And it has downsizing, so, and it also can be referred as divide and conquer. So we try to make that problem smaller and smaller and smaller until we get to a point that it's also called base case, until we get to a point that we know how to conquer, like we know how to solve the problem. And at that point, we're going to backtrack and we can find the solution for the larger problems that we have. In the downsizing, this is the part that we have the self-definition, and it's also known as the recursive step. In the stopping criteria, we don't have any self-definition. We just like solve the problem explicitly. This is the smallest problem that we can get, and at that point we provide an explicit solution to the problem. It's like a little bit vague at this point, I know, but let's see what this means when we talk about examples. So in programming, usually like the first example that we show for recursion is the factorial, how to compute factorial. So if you're not familiar with the notation n factorial is the multiplication of numbers 1, 2, 3 all the way to n. So n factorial is equal to 1 multiplied by 2 by 3 all the way by n minus 1 and then finally n. Okay, now we have already written a program that calculates n factorial using a loop, right? So this is doable without recursion. But we can also look at this problem in this way, so that we can, if f of n is n factorial, we can look at the first n minus 1 terms as n minus 1 factorial. So then f of n is f of n minus 1 multiplied by n, right? So you can think of 4 factorial, for example, as 4 times 3 factorial. And then 3 factorial would be 3 times 2 factorial. 2 factorial would be 2 times 1 factorial. 1 factorial is 1 times 0 factorial. And this can go on. If we keep going, we're going to have like infinite recursion, which is something that we don't want to have. So we have to have a stopping criteria. By definition, we know that 0 factorial is equal to 1. So we can have a stopping criteria defined here. So at this point, we stop. So once we know 0 factorial, then we can find 1 factorial, we can find 2 factorial, we can find 3 factorial, and finally we can find 4 factorial. This is basically how recursion works. We have some recursive step or self-definition step, like where the solution to the problem is defined like by the function itself, but like with a smaller argument. And we also have a stopping criteria, also known as base case. Okay, at this point the base case happens when n is equal to 0. We can write a recursive function in C++ because C++ allows to call a function from within the function itself. This is also true for many other programming languages. As an example, we can write the compute factorial function or factorial function as a recursive function. So previously we have written this program with a loop, but we can also write this as a recursive function, so that like when the parameter is a non-negative number, okay, so it's very important that this is non-negative number. So we just basically write the same definition that we have. If n is equal to 0, we know that 0 factorial is 1, so return 1. Otherwise, call the same function once you have the solution multiplied by n. So this is like, otherwise return n multiplied by compute factorial with a different argument, with the n minus 1 as the argument. So we are calling the same function within the compute factorial function. So here you would have many function calls. So like, let's say like if n is equal to 4 initially, so we're gonna go here at this point. Here we have 4 times, we're gonna call the same function with the argument 3. So the same call stack that we mentioned, anytime you have a function call, you would have a call stack. So like it would be happening again, like we're calling the same function, this time with a different argument. So at this point we're gonna have another n here. This time this n is going to be 3. Again, it comes here, it calls the function again, so it would just like have another function call, so definitely another stack frame. This time n becomes 2, and it goes all the way until n becomes 0. Once n becomes 0, now we can return from the function. It returns from the function, it would replace 1 factorial with 1, and then can return from 2 factorial, can return from 3 factorial, can return from 4 factorial eventually. So this is basically what's happening. I'm going to show you this process again later, but basically the heart of recursion in programming is calling a function within the function. It may seem as an easy task for the compiler or computer to perform recursive task, it is advisable to note that recursive functions are very expensive computationally. So if you can easily replace a recursive function with a non-recursive function, please do so, because recursive functions, like, they have many function calls, and each function call and returning from the function, it takes some extra time. So it's expensive computationally. It is advisable not to use recursive functions if you can replace it with the non-recursive functions. Now, in many programs, recursive algorithms can be very efficient. We're going to see examples of that later in the course. But for example, like this recursive factorial implementation is way more computationally expensive than when you do it with a loop, right? So like here, like this is just like I'm only showing this for your information and like showing you how a recursive function works. But you just have to be aware that uh, recursive functions are very expensive computationally. This is because a function call is computationally expensive process. So there is a concept called function overhead time. It's the time that is spent for calling the function, passing arguments to the function, having like a space allocated in the memory for the function, would have like some local variables, and then also we have to, once we have the answer, we have to return from the function. This is the time that actually doesn't do any useful work for us, but it's required to for the function to do its job, right? Passing the arguments, having memory allocated, returning from the function. This is necessary for the function to do its job, right? But it's not doing any job for us and not doing any useful job for us. So when you call a function, stuff needs to happen to jump to it, then more stuff happens to go back to where you were. So this is called function overhead time. And when you have a recursive function, you would have many function calls, so like gonna have a lot of function overhead time. This is another example of a recursive function, so let's look at it. Here we have two functions. We start always from the main function. The first line in the main function is calling the my function with the argument 3, so counter would be equal to 3. So we have a space in the memory allocated for this function called counter is equal to 3. This condition is not true. We jump here, it's going to print hello 3, and then it calls the same function with a different argument. So this time argument would be 2. So we have another function call. The control jumps to the beginning of the function again. We have another stack frame allocated for this function call. Counter is 2 in this part. This is not true. Again comes here. It would print hello 2. And the next line again calls the same function with a different argument. So this time argument is 1. It would jump here. Another stack frame. This time counter is equal to 1. This is not true. It's gonna jump here. It's gonna print hello 1. And this time it's gonna call the function with the argument 0. So it jumps here. Another stack frame. Counter at this point is equal to 0. So here now counter is equal to 0, so we can return. Once you return, this stack frame is deallocated, right? And the control jumps back to where this function was called with the argument 0. Where was it called? It was called when counter was 1, and it was at this point, right? So this is now done, right? We did my function 0. This is returned. So now it's gonna print cout counter, which is 1, right? So it's gonna print 1. And now it can return from this one. Once it returns from this one, the stack frame that was allocated to this function is gonna be, to this function call is deallocated. Gonna return to where this function was called. Where was it called? It was called at this point where counter was equal to 2, right? So this is done again. Now it's going to print 2. It's going to return. Again, where is it going to return? It's going to return again to the point that the function was called, where counter was equal to 3. So this is done. And then it's going to print 3. And finally, it's going to return to this point, because at this point, the function was called with the argument 3. So this is the end of the program. Another example here. So let's assume that we call this function with the argument 3 for the first time. So we say like print 3, right? So we would have p as equal to 3 first. Like I'm not writing this on the paper, but like I highly encourage you that when you want to analyze this, write it on a piece of paper and try to just like have separate stack frames for each function call, same as like how the compiler does it. So first time we call this function p is equal to 3. This is not true. It's calling the same function with a different argument. So like we have another function called this time, the argument is 2, so p, we jump here, p is equal to 2. Again, this is not true. Then it calls the same function with another argument, this time 1. So you have another function called, this time p is equal to 1. So we start from here, this condition is not true, jumps here. Now another function called, this time the argument is 0, so another function, another stack frame, p is equal to 0 at this point. And now we start from here. Is p equal to 0? Yes, it is. So we return. Once we return, the stack frame that was allocated to this function is deallocated automatically, because we don't have any part of the heap, so everything is going to be deallocated automatically. Once you deallocate from this one, you would go back to where this function was called. This function was called at this point where p was equal to 1. So it's going to get to this point and it's going to print 1, and it would return. Once it returns, again, this function called, this stack frame corresponding to this function call is deallocated, right? And the control goes back to where the function was called. The function was called where p was equal to 2, right? So now this is done. We returned from this, so it's going to print 2. Again, returns from it. So this part of the memory again is deallocated, is released. It's going to go back to where the function was called with the argument 2, so where p was equal to 3, and finally it's going to print 3 and returns from it. So it just basically prints 1, 2, 3. Now I want you to analyze this code when we swap these two lines, and like first like print and first cout and then have the recursive call. I want you to see what happens when we do that. Please analyze this. You should get like 3, 2, 1 this time, so like it's gonna change the order of couting. Another famous example that can be done recursively is Fibonacci series. So here, like if you're not familiar with the Fibonacci series, like first of all, there are two implementations for Fibonacci series. Like this two examples like shows like implementation for one of them. So Fibonacci series, you can think of a series of numbers that the first two numbers, let's say, start with 0 and 1, and any other number, it's going to be made out of the summation of the last two numbers. So the first two numbers is 0 and 1. The one after, it's going to be 1. The one after that, it's going to be 1 plus 1, 2. One after that, 1 plus 2, 3. And then 5, and then 8, and then 13, and then 21, and so on. Okay. The more famous implementation is where you have the first two numbers as 1 and 1. So you have 1 and 1, and then the next number is going to be 1 plus 1, so 2, then 1 plus 2, 3, 5, 8, 13, and so on. These two implementations that we have here assumes that the first series, when the first two numbers are 0 and 1, but like you can easily replace them with the second implementation, with the second series definition. So you see two different implementations of Fibonacci series. So like both of these two functions, they're trying to find the nth number in the Fibonacci series, the nth number in the Fibonacci series, and like assuming that n starts from 0, right? Like, so assuming that the index like starts from 0. In the non-recursive version, we have, you see that like we have 4 variables. One of them is a loop index, and basically we do some manipulation with these variables, and just by doing some mathematical manipulation, we calculate the nth number in the Fibonacci series, and we have a loop, and this is done. Okay, but we can also implement Fibonacci series or this function recursively. So here we just basically say that if n is equal to 0, we have to return 0, because the first number we assumed it's 0. If n is equal to 1, just return 1, because the second number was 1. Otherwise, calculate the last two Fibonacci numbers and add them up and return it, right? So it makes writing the program very easy for the programmer, right? We're putting too much pressure and computational complexity to the compiler, right? Because we have like so many function calls here, but writing it for the programmer is very easy, right? And this is definitely way more computationally expensive than this one, but you can see that like you can write the program with 3 lines instead of having it like with many lines. So this is not time efficient. It's like maybe we can say that it's programmer effort efficient, but it's definitely not recommended if time is very important for us. But you can see that this is like one application of recursion, and here like we have actually 2 recursive calls each time the function is called. So let's say that we want to find the like when n is equal to 3, we want to see like what the Fibonacci number is. So it's gonna go here, n is not 0, n is not 1. It's gonna go here. It says that okay, so first calculate Fibonacci when n is 3 minus 2. So it's gonna call the same function with a different argument. This time n is 1, right? So when n is 1, it's gonna return 1. So now it's gonna return to this function. It knows that this is 1, but then it's gonna call this one. So it's gonna call 3 minus 2, Fibonacci n minus 2. So like it's gonna call the same function, this time with the argument 2. So n is 2, this condition is not true, so again it has to basically calculate Fibonacci 0 first. It's going to calculate Fibonacci 0, it is 0. Then calculate Fibonacci 1, it's going to go here, it's going to calculate it, and it's 1. Now it has the Fibonacci 2, so it's going to return to Fibonacci 2 now. It just basically adds these two and has the answer. You saw that like we had like so many function calls. In different compilers, as far as I'm aware, like we always go from left to right, but in some compilers it might go from right to left. Just wanted to mention this. This depends on the compiler, but I think most compilers, they go from left to right. This is a very good example of like another example of a recursive function. this time I put this here so that we know that here we have like this is something that can happen in recursive functions. So let's say like this is a function that returns true if the argument that you pass to it is prime. A prime number is a number that only divides one and itself. Okay, so it has to divide two numbers. That's why like 1 is not a prime number, because it only divides one number. So this function can be implemented non-recursively, and there are many different implementations for that. Um, like some of them are more efficient than the others, but this time we wanted to implement it recursively. So in order to find if a number is recursive, is prime or not, so like one way of doing it, let's say I want to find out if 7 is prime or not. So I can divide it by 1, 2, 3, 4, or sorry, I can start from 2, 3, 4, 5, 6, 7. If it divides any of the numbers other than itself, it means that it's not prime, right? Because it's not supposed to divide any number other than 1 and itself. Okay, so this is what it's trying to do. Let's call this function with the argument 7, right? So let's assume that we're calling the function with argument 7. I'm only passing one argument to this function, so p is going to become 7. This second parameter has a default value, so it means that if you don't pass any argument to it, it's going to take the default value 2. So I becomes 2. Is 7 equal to 2? No. So it's going to come here and it says like, does 7 divide 2? Like this is the remainder. This is the modulo operator. It's the remainder. Is 7 mod 2 equal to 0? No. Is 7 equal to 1? No. So it's going to call the same function, this time with the same p, but with a different second argument. So it's going to change this second argument to 3. So it's going to come back here this time because we are passing an argument for the second parameter. It's going to overwrite this. So I becomes 3. So this time it's going to check is 7 divides 3. If it doesn't, it's going to call this function again with 7 and 4. It's going to do that again, 7 and 5, 7 and 6, 7 and 7, right? So once we get to the point that I and P are equal, it means that P didn't divide any other number before itself. That means that it's prime, right? So it's going to return 1. And it's gonna go back to the previous function that it was called from, and it's gonna return 1. 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 So always remember that we are making the problem smaller. Once this one is returned, we have to return from all the other functions that were called. Okay, this is something that people forget sometimes, right? Sometimes like people like novice programmers, they forget to put a return here. You always have to put a return here because this function is supposed to have a return type, right? It's supposed to return a boolean, right? You have to do something with whatever it is returned from this. So like the last function call, it's returning 1. The second last one is going to return the same thing. The third last one is going to return the same thing, and this goes on until you get to a point that you had the first function call and you're returning 1 at this point. If p is equal to 8, right? So at the first function call, it's going to return 0, right? So then everything is done, right? So this is basically how this function works. I wanted to show you this using a think I might have this here. Yeah, I might have it here. So here, this is the is prime function. We're gonna see it this time. We're gonna, again, like the same thing that I just mentioned. So you see that we have p, I becomes 2. This wasn't true, so we have another function call. This time p is 7, I is 3. This condition is not true, so it's going to jump here. Another function call, 7, 4. This is not true. Another function call. This is 7 and 5 now. Another function call. This becomes 7 and 6. This is not true again. So another function call. This time comes 7 and 7. Right? If that's the case, it means that this function is going to return 1. Okay? This function returns 1. So now this one also returns 1. Now this one returns 1. Now this one returns 1. Now this one returns 1. And finally this one returns 1, and it's going to print 1 here. Okay, so like I'm showing you this so that you know that once we make the problem smaller and smaller and smaller, we have to come back all the way up to the point that we had the first function call. Right, so like many novice programmers, many new programmers, they forget to put this return here. Many compilers still work with that, but some compilers, they don't work because this function is supposed to return a boolean, right? So like you're supposed to write your program so that like it works in any compiler, right? So like here you have to put a return. This is very similar to the factorial problem that we saw earlier. So this just like calculates the summation of all numbers from 0 all the way to num, or whatever num is, right? And it does it recursively. So this is basically like, I'm not sure if you're familiar with the notation sigma. Just like calculate sigma I, where I changes from 0 to num, right? It calculates that. And so sigma I from 0 to num, it can be thought as sigma I from I equal to 0 to num minus 1 plus num. That's exactly what's happening here. And I'm showing you again the factorial example, right? This is like how you can do it non-recursively, iteratively, using a loop, right? This is how it is done recursively. So with recursively, we make the problem smaller, smaller, smaller. So we have like many function calls, and then we return back, right? So we try to find factorial 4. In order to find factorial 4, we have to find factorial 3, and it's going to make the problem smaller until we get to a base case, right? Until we get to a base case. And then we return 1, we return 1, again return 2, return 6, and so on, return 24 finally. There's something wrong here, because we have to make sure that for this program to work, we have to make sure that n is unsigned, n is positive. So like always remember to put precondition, postcondition. This wasn't the scope of this example, but like always remember that you have to think about like any different cases. What happens if n is negative? Then this function is gonna have infinite function calls, because like it would never get to the base case, right? And if a recursive function doesn't reach the base case, doesn't have any stopping criteria, what happens? We're gonna have infinite memory calls. So at one point we run out of memory, we run out of stack, The stack is the part of the memory that's allocated in function calls, right? So we're gonna run out of it. It's gonna be called stack overflow. Stack overflow, sorry. Stack overflow, and then it just basically you would have a runtime error, and your program would stop because of running out of memory. Okay, so that's basically what's happening when you have a recursive function without any base case, without any stopping criteria. Another example we see here, it's like we try to implement the power function, so like raising n to power k. Again, you can do this using a for loop or a while loop. It's possible to do it using loop, but also it is possible to do it recursively. So you can think of, like, let's say if n is 10, n is 2 and k is 10. If you want to find 2 to power 10, you can think of 2 to power 10 as 2 times 2 to power 9. You can think of 2 to power 9 as 2 times 2 to power 8. And you can do that until your k becomes 0. At this point, you have the answer. So this is your base case. If k is equal to 0, return 1. Otherwise, find n times the same function, but n and k minus 1. Okay, this is not a very efficient implementation. Don't think that, like, because we have put this here, like, this is efficient. This is definitely not efficient. And don't think that because it doesn't have any loop, it's efficient. No, the loop is implicit in the function calls that we have. Like, we are calling a function many times and we are returning from it. So definitely the non-recursive version of this problem is more efficient than this one. This is just like to show you how recursion works. So this example, I want you to think about it and like think like how this works, and like what is the what does this function do. Actually, I can tell you this. If you guys have passed the discrete math course and you have seen the Euclidean algorithm for calculating the greatest common divisor of two numbers, this is the implementation for that, right? This is the implementation for the Euclidean algorithm, and it's a recursive implementation. And here I'm showing you this variable to show you like how many function calls we have, how many recursive calls we have, like what is the depth of recursion, right? So this is basically what this variable is used for. Every time it's called, it's going to be incremented. And the first time it's called, like, we're not going to pass any argument for it. It's going to have a default value, right? So maybe I should show you this, and like I'll like try to see if it works. So the first time we call the function, m is 77, n is 28. Another function call, sorry, the first function call, now we're passing the parameters. 77 and 28 are x and y, and depth by default is 1. We have a local variable result, it's like 77. This condition, it is true, y is not 0, right? So then it's going to call the function again. We have x and y, 28 and 21. So like we're passing 20y and like x mod y. X mod y was 21. So again, result is calculated. Then another function call. This time x would become 21 and y becomes 7, right? Depth is 3. We go here, this condition is still true, it's gonna call another function. So this time x becomes 7, y is 0. So we are at this point, right? Now this condition is not true anymore because y is 0. So this is our base case, right? This is like, this one is our base case. This is like how we guarantee that we don't have infinite function calls. So now it's going to return. What is it going to return? It's going to return 7. So it went, sorry, it just returned 7. And now, like, this is done. This function call is done. We have returned from it. So it goes to next line and return result again. So it's gonna return from this one, it's gonna return from the next one, it's gonna return from the next one. You see that all the local variables and like are deallocated, and finally it's gonna print the greatest common divisor of the two numbers and returns. It was a good example for recursion, also a review of your discrete math knowledge. This is another recursive problem. So I try to put like many examples, so this is reviewed for everybody. This problem tries to separate the digits of a number. Like, it doesn't matter how many digits it has, like it tries to do that. This is the non-recursive version. This is the recursive version. So like this one is using a loop. This one, it just basically says that, okay, it just basically tries to, sorry, I think it's gonna be, yeah, so it's try to like divide it by 10, right? So like, let's say like the first time, like n is 1234. This is not true, so it's gonna come here, it's gonna call the function with the argument 123. It's gonna come here, it's gonna call the function with argument 12. It's gonna call the function with argument 1, and now this is true, so it's gonna print 1. It's gonna come back here, right? So n was 12, it's gonna print n mod 10, which is 2, and then it's, sorry, this is, yeah, so this is done. This is going to print 2. It's going to come back here to where this was done. It's going to so like it was 123, so now it's going to print 3, and then it's going to come back, it's going to print 4 eventually. So this is basically how the function works. Like, it prints 1, 2, 3, 4. Just like separates the digits and prints them vertically. Try to analyze it on a piece of paper. First, try to write it yourself, like see if you can write it yourself. I'm gonna stop at this point and explain the recs in a different video. Thank you so much.